I want you to imagine just for a second that you're stepping outside into the freezing night air. But you're not walking out of a modern apartment building, right?
Right, no streetlights, none of that.
Exactly. There are absolutely no streetlights washing out the sky with that dull orange haze. You are stepping out of, like, a primitive shelter, or maybe a cave, tens of thousands of years ago.
Just completely in the dark.
Yeah, you're standing in the wet grass before a single mathematical equation has ever been written down, before anyone on Earth even had a name for any planet. And, you tilt your head back, and what do you see?
You'd see this overwhelming, just terrifyingly dense canopy of light.
Yeah, the Milky Way isn't just some faint smudge. It is a blazing river cutting straight across the dark. And here's the reality of your situation. Your survival absolutely depends on understanding what you're looking at.
It really is the perfect place to start, I think, because it completely strips away all of our modern comfort. For early humanity, astronomy was not a hobby.
No, not at all.
It wasn't, an academic pursuit carried out in these sterile observatories. It was literally a matter of life and death. The sky above you was your clock.
Right.
It was your compass, your calendar, and your mythology, all just rolled into one. I mean, if you didn't know how to read the phases of the moon or track the subtle shifting of certain constellations as they rose and set, you simply didn't know when the seasons were turning.
And, if you don't know the seasons, you just don't survive.
Exactly.
If you misread the weather and plant your seeds too early, a late frost just wipes out your entire food supply.
Yeah.
If you don't know the stars, you don't know when the animal herds are migrating, or, when the ocean tides are shifting to make coastal foraging safe.
It was pure survival.
Right. So humanity started looking for patterns. We had no telescopes, no computers, none of that modern instrumentation.
Yeah.
We just had patience and our raw biological senses and that desperate survival-driven need to recognize patterns among the stars is, it's the foundation of what we're doing today.
It really is.
So you're listening to a deep dive where we are unpacking this really fascinating, independently produced audio script called Cosmos, a companion journey. And our mission today is to figure out how we went from shivering in that cave, trying to predict the rain, to literally mapping the edge of a black hole.
Which is just an astonishing trajectory when you really think about it. And, this text presents a profound philosophical thread that kind of anchors everything we're going to explore today. It's the paradox of the observer.
Paradox of the observer, right.
Yeah, think about your own existence for a second. We are made of the universe, right? We are matter that has basically woken up to look back at itself. But our senses are strictly local.
Very local, yeah.
Like you can only see as far as the physical light entering your retina allows. You can only touch what is immediately in front of you. Your life, in the grand scheme of cosmic time, is incredibly brief.
Just a blank.
Right, a blink. Yet, despite being confined to one tiny rock, through shared records in mathematics and eventually these incredibly complex machines, we somehow figured out how to extend our local senses to the very edge of reality.
But that transition from local senses to cosmic understanding, it definitely didn't happen overnight.
No, not at all.
And it definitely didn't happen in just one place either. I feel like when we learn about early astronomy in school, it's so easy to fall into this trap of thinking it was just a single straight line of progress.
Yeah.
Usually focused in ancient Greece or Renaissance Europe.
Right, the classic Western narrative.
Exactly. But we have to elevate that view.
Mm.
The history of reading the sky is actually this massive collection of brilliant, independent conversations happening all over the globe. And they're all interacting with the exact same raw data.
You see this globally, you really do. Look at the Babylonian scholars in Mesopotamia. They were painstakingly tabulating planetary motions on clay tablets using cuneiform script.
Wow, yeah.
And what's really fascinating about the Babylonians is that they didn't try to build geometric models of the solar system like the Greeks did later. They just used pure arithmetic. They found the mathematical rhythms in the sky to predict lunar eclipses with, frankly, astonishing accuracy.
And while they're doing that in the desert, you've got Chinese astronomers who are meticulously recording what they called guest stars.
Oh, I love the guest stars.
Right. These were sudden, brilliant points of light that would just appear out of nowhere, burn really brightly for a few months, and then fade away. And they recorded one in the year 1054 AD that was so bright it could be seen during the daytime for nearly a month.
Which is incredible to think about.
It is. And we now know, because we pointed modern telescopes at that exact coordinate, that they were actually watching the supernova explosion that created the Crab Nebula. They were literally logging stellar death.
Yeah, they were documenting the end of a star. And then you also have Indian mathematicians who were refining these incredibly complex calendars and planetary models, pushing trigonometry to new heights just to track the heavens.
It's all connected.
It is. And, we absolutely cannot talk about early astronomy without talking about the Polynesian navigators. They accomplished some of the most staggering feats of human exploration in history.
Oh, absolutely.
They weren't just looking at the stars. They were integrating the sky with the ocean. They memorized this mental compass of rising and setting stars, and then they combined it with the ability to read wave refraction.
Wait, reading wave refraction?
Yeah, literally feeling how deep ocean swells bounced back off distant, unseen islands.
Yeah.
And they used that to navigate across thousands of miles of the open Pacific Ocean.
That is just mind-blowing. They're basically using their entire environment as a giant astronomical instrument.
Exactly.
But eventually, this global practical interaction with the sky hits a shift. There's this moment where astronomy moves from storytelling and mythology and, pure survival into something far more rigorous, the birth of the scientific method.
Right. And the transition is actually surprisingly subtle. It wasn't some sudden flash of genius. It was simply the decision to keep watching after a story had been told.
Yeah, imagine inheriting a sky with no labels. You see a bright point of light low in the west, it disappears into the sun's glare, and then months later, a bright point appears in the east.
Right, so what is it?
Exactly. Is it the same object? How can you actually be sure? A mythology might say it's two different gods. But science demands a reliable pattern. Knowledge only really begins to grow when a claim risks failure. That is the essence of the method right there.
The risk of being wrong.
Exactly. The pattern has to return in new data, under new conditions. You literally have to hand your findings over to a group of people who would actually be rewarded for proving you wrong.
And you have to accept whatever answer the sky gives you, even if it completely wrecks your worldview. Which, I guess, leads us to arguably the most dangerous astronomical discovery in human history.
Oh, definitely the death of the geocentric universe.
Right, the idea that Earth was the fixed, unmoving center of everything. But, I want to pause here for a second, because modern people always look back at the geocentric model and treat it like it was just ancient ignorance or like religious stubbornness.
Right, they dismiss it.
Yeah, but if we're being honest, wasn't the geocentric model actually the most perfectly logical conclusion based on ordinary human experience?
It was entirely rational. I mean, think about your physical reality right now. When you stand outside, the ground beneath your feet feels completely stationary. You don't feel like you're hurtling through space at 67,000 miles an hour.
No, I definitely feel pretty still right now.
You feel still, and when you look up, you literally watch the sun, the moon, and the stars wheel around you. A geocentric cosmos matched ordinary human intuition perfectly. The Greeks, specifically Ptolemy, codified this into a massive, highly predictive system.
Right. I mean, if I drop a rock, it falls straight down to my feet. If the Earth were spinning, shouldn't the rock land like 10 yards behind me while the Earth moves underneath it?
Yeah.
That was the common sense of the time.
Absolutely.
But the problem is, nature doesn't really care about our common sense. As astronomers kept watching, the math started getting incredibly messy.
It did, and specifically because of something called retrograde motion. Most of the time, planets drift eastward against the background stars, but every once in a while, planets like Mars will appear to slow down, stop, move backward toward the west for a few weeks, and then resume their normal path.
Like it just threw it in reverse.
Right. And if Earth is the center of everything and everything orbits us in perfect circles, a planet suddenly throwing it in reverse makes absolutely no sense.
So to fix this, Ptolemy had to invent these things called epicycles, which is basically the idea of wheels within wheels. Mars isn't just orbiting Earth, it's orbiting on a tiny invisible circle, which is itself attached to a larger circle orbiting Earth.
It was a very complicated workaround.
Yeah, and as centuries went by, to make the predictions match the real sky, astronomers had to keep adding more and more invisible wheels. The math just became an absolute nightmare.
Which is when Nicholas Copernicus finally suggests a simpler mathematical solution. He says, What if we just put the sun in the center? What if Earth is just another planet?
Which changes everything.
It does. Suddenly, retrograde motion is perfectly explained. It's just an optical illusion. It's caused by Earth, which is moving faster on an inside track, lapping a slower outer planet like Mars.
Oh, like passing a car on the highway.
Exactly. As we pass it, Mars temporarily looks like it's moving backward against the background stars.
But Copernicus knew how dangerous this idea was, right? I mean, he didn't even publish his full theory until he was literally on his deathbed.
Yeah.
Because if Earth is just another planet, then humanity isn't the focal point of creation.
It was a very dangerous thought.
Yeah. And then Tycho Brahe comes along. Now, he doesn't have a telescope because they haven't been invented yet. But he builds these massive brass quadrants and measures the exact positions of the planets for decades with just unprecedented naked eye precision.
And that data is the key. Tycho's assistant, Johannes Kepler, inherits those decades of meticulous measurements. And Kepler spends years trying to make Mars's orbit fit into a perfect divine circle.
Because that was the expectation.
Right, but the data refuses to fit. It's off by just 8 arc minutes, which is a tiny fraction of a degree. A lesser scientist probably would have just ignored it. But Kepler trusts the data over his own desires. He realizes the planets don't move in circles at all. They move in messy, stretched-out ellipses, speeding up as they get closer to the sun and slowing down as they move away.
And the final nail in the coffin comes from Galileo. He builds this rudimentary telescope, points it at Jupiter, and sees 4 tiny points of light hovering around it. Night after night, he watches them move. He realizes they are moons orbiting Jupiter.
Which completely shatters the glass ceiling of ancient astronomy.
Exactly. Because if moons are orbiting Jupiter, then not everything is orbiting Earth. There are other centers of gravity out there.
The shift required just a complete rewiring of human perspective. Picture a passenger standing on the deck of a massive ship slowly pulling out of a harbor. If the water is perfectly smooth, the passenger feels completely still. To their eyes, it looks like the coastline is sliding backward away from them.
Right.
Perspective imitates structure. Astronomy had to learn to separate what the sky appears to do from what the physical bodies are actually doing. We had to completely decouple human intuition from reality.
And that decoupling reaches its absolute peak with Isaac Newton. Newton basically sits down, invents a new branch of mathematics called calculus, looks at an apple falling from a tree, looks up the moon, and proves that they are doing the exact same thing.
This is where Newton just shatters the final barrier. Before him, people believed the Earth was governed by one set of physical laws, and the heavens were governed by a different divine set of laws.
Right, 2 separate domains.
Yes. But Newton proved that the exact same invisible force pulling the apple to the dirt is the force constantly pulling the moon. The moon is literally falling toward Earth, but it's moving sideways so fast that it constantly misses the ground. The universe is governed by universal laws.
It gives humanity immense predictive power, but we lose the comfort of centrality forever. We're not the center. The Earth is moving, and once you accept that we're just one rock orbiting the sun, it naturally forces the next question. Exactly how vast is our local neighborhood?
It's a daunting question.
It really is, because we've all seen the neat, tidy diagrams in school textbooks, or those mechanical models with the brass gears where all the planets are nicely lined up right next to each other. Those models completely lie to us. The scale of the solar system is something the human brain truly struggles to comprehend.
Because if you build a scale model that accurately represents the sizes of the planets, the distances between them become impossible to fit in a normal classroom.
Right, let's use a tangible thought experiment. Imagine you place a standard-sized grapefruit on a table in an open field. That grapefruit is the sun. Where is Earth in this model? Earth is a single grain of sand, and it is located roughly 10 meters, so about 30 feet away from the grapefruit.
30 feet away.
So you have grapefruit 30 feet of completely empty space and then a grain of sand. But what about the outer edges? What about Neptune?
In that exact same model, Neptune, the outermost major planet, is located hundreds of meters away. It is several football fields out from your grapefruit, and it's just the size of a coffee bean.
Wow.
The overwhelming defining characteristic of our solar system isn't the planets, it is the staggering, freezing emptiness between them.
The space is so vast that miles and kilometers just become useless. We have to use light as a metric of distance. Light travels at the absolute speed limit of the cosmos, which is roughly 186,000 miles per second.
Incredibly fast.
Right, and at that speed, sunlight takes about 8 minutes to reach that grain of sand we call Earth. If the sun were to magically vanish right now, we wouldn't know about it for 8 minutes. We'd still see it shining in the sky. We'd still feel its gravity.
Yeah.
But by the time that same light travels all the way out to Neptune, it has been flying through the void for over 4 hours.
4 hours of travel at the speed of light. And that massive expanse wasn't always a quiet, stable system either. The history of our solar system is incredibly violent.
Oh, yeah.
The planets didn't just quietly form in the orbits they have today. We now have strong evidence of planetary migration. In the early days of the solar system, massive gas giants like Jupiter and Saturn likely drifted inward toward the sun, wreaking just massive gravitational havoc, scattering smaller bodies everywhere before drifting back out to their current positions.
It was essentially a cosmic billiards table. And what we have left today is a highly diverse neighborhood. Close to the sun, you have the inner rocky world, so Mercury, Venus, Earth, and Mars. Out in the freezing dark, you have the massive gas and ice giants. And drifting all throughout this ocean are the leftovers, the asteroids and comets.
And those leftovers are scientific gold mines. They're the pristine, untouched puzzle pieces from the birth of our solar system 4.5 billion years ago. That is exactly why missions like OSIRIS-REx are so critical.
Yeah, that mission is amazing.
We didn't just photograph an asteroid. We literally flew a spacecraft to a near-Earth asteroid named Bennu, matched its orbit, dropped down to the surface, and fired a burst of nitrogen gas to kick up dirt and catch it. We brought physical, primitive material back to Earth laboratories. We are literally holding the dawn of the solar system in our hands.
Which is just an incredible segue into how we actually explore this massive ocean around our star. I mean, our biological bodies are incredibly fragile. We require very specific temperatures, pressures, and atmospheres to survive. We simply can't survive out there.
No, we cannot.
So we build machines. We extend our senses into places human bodies cannot go. When Voyager probes pierced the edge of the heliosphere, which is that massive magnetic bubble created by the solar wind that protects our system from interstellar cosmic rays, it was a human triumph.
It is the ultimate extension of the observer. We have rovers the size of cars driving across the surface of Mars. They are equipped with lasers that vaporize rock to read its chemical composition, proving beyond a doubt that water once flowed across that barren surface.
Wow.
They are driving over dry river channels and drilling into sedimentary rock. And even further out, we have probes studying Jupiter's moon Europa and Saturn's moon Enceladus.
Which are completely covered in ice, right?
Covered in ice, yes, but what the probes detected is staggering. Through the mechanism of tidal heating, where the massive gravity of Jupiter and Saturn literally squishes and stretches these moons as they orbit, creating internal friction, there is so much heat inside them that beneath miles of ice, there are global liquid water oceans.
Global oceans.
Yes. Enceladus is actively spraying geysers of salty water and organic molecules straight out into space. We flew a probe through those plumes to taste the water.
But wait, if Enceladus is out near Saturn, and Saturn is roughly 1 billion miles away, how are we flying a probe through a geyser? I mean, how does controlling these distant machines actually work? If you have a rover on Mars and it's driving toward a cliff edge, you can't just sit in a control room in Houston and hit the brakes on a joystick in real time, right?
You absolutely cannot. And this introduces a brilliant concept from the text called the delayed wager. Because radio signals are essentially just light waves, they are bound by that cosmic speed limit. Depending on where Mars and Earth are in their respective orbits, a signal can take anywhere from 4 minutes to over 20 minutes just to travel one way.
So if a camera on the rover sees a cliff and transmits that image to Earth, it takes 20 minutes for the engineers to see it. If they instantly panic and send a command that says, "Stop P," it takes another 20 minutes for that command to reach the rover. That's a 40-minute round trip. So if the rover was driving toward the cliff, it has been sitting at the bottom of a crater for 39 minutes by the time the stop command actually arrives.
Precisely. Distance turns every single command into a wager against time. This is why robotic autonomy is not just some technological luxury. It is the absolute foundation of deep space survival. Take the Mars rovers. During entry, descent, and landing, which is often called the 7 minutes of terror.
I've heard of that, yeah.
Yeah, the spacecraft hits the Martian atmosphere at 12,000 miles an hour. It has to deploy supersonic parachutes, fire retro rockets, and lower the rover on a sky crane, all completely on its own. Mission control can do nothing but sit in agonizing silence, waiting for the signal that says, "I survived."
It's just an incredible engineering feat. The intelligence of the observer has to be pre-programmed into the machine. But let's keep moving outward.
Oh.
If we zoom out past Neptune, past the Voyager probes, the sun shrinks down until it's just another point of light, becomes just one star among roughly 200 billion others. We arrive at the Milky Way, our galaxy.
Yes, the Milky Way.
And there is a truly fascinating paradox here. You can go online right now and find thousands of gorgeous spiraling images of the Milky Way galaxy. But every single one of them is an illustration. We have never, ever seen the Milky Way from the outside.
It's a profound constraint, really. Every map of our galaxy, every rendering of its spiral arms is an act of meticulous reconstruction from the inside. Imagine trying to map an enormous, dense forest while you're standing right in the middle of it.
Right.
You can see the trees immediately around you, but the nearby trunks block the distant ones. You can't just float above the canopy to get the big picture.
And in the Milky Way, the trunks blocking our view are massive clouds of cosmic dust and cold gas. If you use a standard optical telescope, so the kind that sees the visible light our human eyes can process, the center of our galaxy is completely obscured by these dark, sprawling clouds. So to map the forest, astronomers had to invent tools for the dark.
They had to look at the universe across the entire electromagnetic spectrum. We combine radio waves, infrared light, X-rays, and gamma rays. Infrared is particularly crucial because its longer wavelengths allow it to slip right through the microscopic dust grains that block visible light.
Oh, that makes sense.
Suddenly, the dark clouds become transparent, and we can map the galaxy's true form by tracking the motion and distance of billions of stars.
And when we talk about tracking stars, we really have to talk about the European Space Agency's Gaia mission. This is arguably one of the most important astronomical missions in history. By the time it ends its science operations in early 2025, Gaia will have mapped roughly 2 billion stars.
2 billion, yes.
And it doesn't just take a picture. It measures their exact positions, distances, and motions using a technique called parallax.
Parallax is actually something you experience every day. If you hold your thumb out at arm's length, close your left eye, and look at your thumb against the background of the room, it appears to be in one spot. If you switch and close your right eye, your thumb appears to jump horizontally.
But the thumb didn't move.
Right, the thumb didn't move. Your perspective shifted by the distance between your eyes.
Right, and Gaia does this on a cosmic scale. Instead of the distance between human eyes, Gaia uses the orbit of the Earth. It measures a star, waits 6 months for the Earth to travel to the opposite side of the Sun, which is a baseline of 186 million miles, and then measures the star again. The tiny apparent shift in the star's position against the background galaxies tells us exactly how far away it is.
And by tracking how those 2 billion stars are moving, Gaia is revealing the violent history of the Milky Way. We can literally see streams of stars moving together at odd angles, which are the gravitational scars of ancient galaxy mergers. The Milky Way has grown by cannibalizing smaller dwarf galaxies over billions of years. It is a highly dynamic, active structure.
And if you follow those stellar orbits all the way into the absolute center of the galaxy, you find the engine in the dark. Sagittarius A. For decades, astronomers cracked a specific star, called S2, orbiting an invisible point at the center of the galaxy. But S2 was moving at a fraction of the speed of light. To whip a star around that fast, whatever invisible object was pulling on it had to have the mass of 4 million suns, packed into a space smaller than our solar system.
A supermassive black hole.
Exactly.
And we didn't just stop at calculating its mass either. Recently, the Event Horizon Telescope collaboration achieved the impossible. Using a technique called Very Long Baseline Interferometry, they linked radio observatories all across the globe, from Hawaii to Antarctica, to create a virtual telescope the size of the Earth itself.
Wow.
They aimed it at the center of the galaxy and actually captured an image of the glowing, superheated gas ring swirling right at the edge of that black hole.
We took a picture of a shadow cast by gravity. It's just stunning. But if you take those same powerful telescopes and point them away from the dense center of the Milky Way out into the deep, dark patches of the night sky where it looks like there is absolutely nothing, what happens? You do a long exposure like the famous Hubble Deep Field. You stare at a patch of sky the size of a grain of sand held at arm's length.
You find that emptiness is usually just a failure of sensitivity. When Hubble stared at that apparently empty darkness for days, the image it returned was littered with light. But they weren't stars. There were thousands and thousands of entire galaxies, spirals, ellipticals, irregulars, each containing hundreds of billions of stars of their own.
And as we map these galaxies on the largest possible scales, we realize they aren't just scattered randomly like salt on a table. Gravity has sculpted them. We're talking about the macrostructures of the universe, the cosmic web.
When you zoom all the way out, the universe looks remarkably like a vast biological neural network. Gravity has drawn matter into these unfathomably large structures. You have massive clusters of galaxies connected by long, glowing filaments intersecting at cosmic nodes. And between these filaments are immense, underdense voids of nearly empty space.
But there is a massive problem here, isn't there? If you count up all the visible light, every star, every glowing cloud of gas in those clusters, it is not enough. The gravity of the visible matter is nowhere near strong enough to hold these massive structures together. The galaxies are spinning so fast that they should literally fly apart and scatter into the void.
This is where we run into one of the greatest enduring mysteries in modern physics: dark matter. The visible matter simply does not provide enough mass to explain the observed motion. But it's important to clarify how we know this, because we didn't just invent dark matter to make the math work. It is strongly inferred through multiple independent lines of evidence.
The most dramatic being gravitational lensing, right? Einstein predicted that mass literally bends the fabric of space-time.
Exactly. Imagine looking through the curved base of a wine glass. The light behind it gets stretched and distorted. On a cosmic scale, a massive cluster of dark matter does the same thing. It bends the space-time around it. When light from a more distant background galaxy passes through this warped space, the light is stretched into arcs, or even complete rings, which we call Einstein rings.
Oh, that's wild.
By mapping exactly how the light is distorted, astronomers can calculate exactly how much mass is doing the bending and map the invisible dark matter structure.
So we can map the invisible by how it manipulates the light. But the catch is, while its gravitational effects are undeniable, its actual particle identity remains completely unknown.
Right. Completely unidentified.
It doesn't interact with electromagnetism, it doesn't emit light, reflect light, or block light. We know it acts gravitationally, but we have absolutely no idea what it actually is.
It is a profound reminder of our disciplined uncertainty. But let's dive back from the macro to the micro for a minute. Let's zoom from the massive cosmic web down into the galaxies themselves, into the cold molecular clouds where the stars that light up this web are actually born. Because everything we are, our biology, our planets, is deeply tied to stellar evolution.
We are star stuff. Every single carbon atom in your cells, every atom of oxygen you're breathing right now, was forged in a cosmic furnace older than the Earth.
So let's talk about how a star operates. It begins in a massive freezing cloud of molecular hydrogen. Eventually, a pocket of this gas becomes too dense and collapses under its own gravity. As it compresses, it heats up, forming a protostar.
And as it continues to crunch inward, the core temperature reaches millions of degrees. At this point, the hydrogen atoms are moving so fast and are packed so tightly that they overcome their natural electrical repulsion. They smash together and fuse into helium through the proton chain.
And that's fusion.
Yes. This nuclear fusion releases a staggering amount of energy. A star is born. And from that moment on, the entire life of the star is a brutal, delicate negotiation between two opposing forces. Gravity is constantly trying to crush the star inward. The nuclear fusion in the core is radiating immense energy, pushing outward. For billions of years, in the case of our sun, that negotiation holds in perfect hydrostatic equilibrium.
But the star's initial mass dictates its ultimate fate. Small, red dwarf stars are frugal. They sip their hydrogen fuel incredibly slowly, and they will burn for trillions of years. But the massive stars, the ones 8, 10, or 20 times the mass of our sun, they are the furnaces. They burn incredibly bright, live fast, and die young. They burn through their hydrogen in just a few million years.
And when they run out of hydrogen, gravity starts winning. The core shrinks, gets even hotter, and starts fusing heavier elements. Hydrogen fuses into helium, helium fuses into carbon, then oxygen, neon, silicon, all the way up the periodic table. And we can actually prove this from light years away using spectroscopy.
Spectroscopy is truly the barcode scanner of the universe. It relies on the quantum mechanics of the atom. Electrons orbit a nucleus in very specific, distinct energy levels. When an electron jumps down to a lower level, it emits a photon of a very specific color. When it jumps up, it absorbs a specific color. By capturing a star's light and splitting it through prism into a spectrum, we can look for the dark lines where specific colors have been absorbed.
Like a barcode.
Exactly like a barcode. Those lines tell us precisely which chemical elements are present in the star's atmosphere.
It's how we know exactly what these cosmic furnaces are cooking up. But eventually, the massive star hits a brick wall. It fuses silicon into iron. Iron is the ultimate ash of the cosmic furnace. Fusing iron requires more energy than it releases, so the outward pressure of nuclear fusion abruptly stops. In a fraction of a second, gravity wins the negotiation completely. The massive core collapses inward, hits the iron core, and rebounds outward in a colossal supernova explosion.
The outer layers of the star are blasted across the galaxy, but what remains in the center is governed entirely by mass. If the core is roughly between 1.5 to 3 times the mass of our sun, the collapse crushes the atoms so violently that the electrons are driven straight into the protons. They combine to form a solid sphere of neutrons. You're left with a neutron star.
The physics here are just terrifying. You have an object with more mass than our entire sun, but it has been crushed down to a sphere roughly the size of a city, say 10 or 12 miles across. The density is incomprehensible. If you could somehow safely scoop up a single teaspoon of neutron star material and bring it to Earth, that teaspoon would weigh billions of tons. It would fall straight through the crust of the Earth.
It absolutely would, and because the core collapsed so drastically, it conserves its angular momentum, just like an ice skater pulling her arms in to spin faster. Some neutron stars rotate hundreds of times per second. They possess terrifyingly strong magnetic fields that sweep beams of radiation across the sky. If those beams sweep over Earth, we detect them as rapid, perfectly timed pulses of radio waves. We call them pulsars. They are the most precise cosmic clocks in the universe.
But what if the collapsing core is even heavier? What if it's more than 3 solar masses? Then not even the quantum pressure of neutrons can hold up against gravity.
Then the collapse never stops. The matter crushes down to a point of infinite density. It tears a hole in the fabric of space-time. It becomes a black hole.
Surrounded by the event horizon.
Yes, and we must be precise about what the event horizon is. It is not a physical surface. You cannot touch it. It is a causal boundary. It is the exact spherical threshold where the escape velocity required to leave the gravitational pull exceeds the speed of light. Because absolutely nothing in the universe can travel faster than light. Once you cross the event horizon, you can never return. Every path through space-time inside that boundary curves downward toward the singularity. The inside is causally disconnected from the rest of the universe.
Which is deeply unsettling. And we know they exist not just from images, but because we have literally felt them collide. In 2015, the LIGO Observatory detected gravitational waves for the very first time. 2 massive black holes spiraling around each other over 1 billion light years away finally collided and merged.
The energy released in that collision was greater than the light of all the stars in the observable universe combined, but it was released entirely as invisible ripples in the fabric of space-time. To detect it, LIGO uses laser interferometers. They split a laser beam down 2 L-shaped arms, each miles long, and bounce them off mirrors.
Right.
When a gravitational wave passes through the Earth, it literally stretches and squeezes the space the lasers are traveling through. The detectors measured a change in distance smaller than 1/10,000th the width of a single proton.
It's an engineering miracle. We essentially built an ear for the universe. We don't just see the cosmos anymore, we can hear the gravity of black holes colliding. Now, whenever black holes and warp space-time come up, people always point to that classic science class analogy. You know the one? You take a stretched rubber sheet, drop a heavy bowling ball in the middle, and it sags down. Then you roll a marble, and it spirals down toward the bowling ball. It's universally taught to explain Einstein's gravity.
I'm so glad you brought this up because we really need to deconstruct that analogy. It is useful as a very basic entry point, but if you look closely at it, it is philosophically and physically broken.
Right, because why is the bowling ball sinking into the rubber sheet in the first place? Why is the marble rolling down the slope?
Exactly. They are sinking because the Earth's external gravity is pulling them down in the room you are standing in. The analogy requires an external downward force of gravity to explain the concept of gravity. It's entirely circular. In reality, space-time does not have a downward orientation.
So what's actually happening then?
The rubber sheet only represents 2 dimensions of space. But real geometry and general relativity operates in 3 dimensions of space and 1 dimension of time. When a massive object like a star or a black hole curves space-time, it is not just warping physical space, it is warping time itself. Gravity is largely the result of time moving slower, closer to a massive object.
Wow.
The marble isn't rolling down a physical hill, it is following the straightest possible path through a 4-dimensional geometry where time and space are bent.
So an analogy can open the door, but it shouldn't become the room. Eventually, you have to embrace the complex mathematical reality. And that reality, the destruction of these dead stars, the supernovae, the neutron star collisions, is what scatters all those heavy elements out into the void. The carbon, the iron, the calcium, the very elements required for biology, which naturally shifts our focus to where those elements end up. They accrete into disks around new stars, and they form planets.
For most of human history, planets outside our solar system, exoplanets, were purely philosophical constructs. We assumed they were out there, but we had absolutely zero empirical proof.
Right now.
That has completely changed. As of July 30, 2026, the NASA Exoplanet Archive lists 6,333 confirmed exoplanets. Over 6,000 distinct measured worlds orbiting other stars.
In a single human lifetime, we went from philosophy to a packed cosmic census. And the way we find them is wildly clever because we almost never see the planets themselves.
Right.
The glare of their host star is billions of times too bright. Instead, we use the transit method. It's like staring at a massive, blinding searchlight from hundreds of miles away and waiting for a tiny moth to fly across the beam.
It requires stunning precision. When a planet's orbit happens to be aligned perfectly edge-on with our telescopes, it will pass directly between us and its star. We measure the microscopic dip in the star's light as the planet blocks a fraction of it. If that dip repeats on a perfectly regular schedule, we know a planet is orbiting. From the amount of light blocked, we can calculate the planet's exact size. From the time between transits, we calculate its orbital distance.
And there are other methods that measure gravity instead of light, too. The radial velocity method or the Doppler method.
Yes, gravity is a two-way street. The star pulls on the planet, but the planet also pulls back on the star, causing the star to wobble slightly in space. We detect this wobble through the Doppler effect. It's the same physics as hearing a police siren speed past you. As the siren moves toward you, the sound waves are compressed, creating a higher pitch. As it moves away, they are stretched, creating a lower pitch.
And light does that, too.
Light does the exact same thing. As the star wobbles toward us, its light waves compress and shift toward the blue end of the spectrum. As it wobbles away, the waves stretch and shift red. By measuring that microscopic color shift, we can weigh the invisible planet pulling on the star.
And some missions even use coronagraphs, which are physical disks placed inside the telescope to perfectly block the star's blinding light, allowing us to directly photograph young, massive, glowing planets out in the dark. And what this census of 6,333 worlds has taught us is that our solar system is not the standard template. The universe is endlessly, wildly creative.
We have discovered hot Jupiters. These are gas giants more massive than our Jupiter, but orbiting so close to their stars that they complete a year in a matter of days, their atmosphere is literally boiling away into space. We found incredibly compact systems where 5 or 6 rocky planets are crammed into an orbit smaller than Mercury's. We have super-Earths, rogue planets drifting through the dark with no star at all, and planets orbiting binary star systems with 2 suns in their sky.
Which brings us to the ultimate question. If the galaxy is teeming with planets, and the heavy elements necessary for life are scattered everywhere, what about biology? How does life actually emerge from this chemistry? The text defines life in a very physical way, as a matter that learned to preserve information and act on its environment.
It is a profound shift in perspective. Life is not some magical substance completely separate from the universe. It is a complex chemical process governed by the same physical laws as a star. On Earth, life solved the problem of preserving information by utilizing incredibly complex molecules, DNA and RNA. Evolution by natural selection acts on the constant, tiny variations in that molecular information.
But the text is very careful to correct a common misconception here. We constantly hear DNA referred to as a blueprint, the blueprint of life. But that is the wrong way to think about it. DNA is not a static architectural blueprint. It is a library.
The distinction is vital. A blueprint is rigid. It is a one-to-one diagram. If the blueprint indicates a wall goes here, you build a wall there. But DNA is a vast library of instructional manuals used by a living, interacting system, the cell.
Right.
The environment, epigenetic markers, and the history of the organism dictate which books are pulled off the shelf, when they're read, and how they're translated into proteins. It is heavily context-dependent. The environment interacts with the genome dynamically.
And that dynamic interaction led to massive planet-altering evolutionary milestones. Life didn't just passively exist on Earth, it terraformed it. Billions of years ago, the atmosphere had almost no free oxygen. Then, cyanobacteria evolved the ability to perform photosynthesis. They started exhaling oxygen as a waste product.
The Great Oxidation Event. It was the first massive pollution crisis on Earth. Oxygen was highly toxic to almost everything alive at the time. It caused a mass extinction, but it eventually forced the evolution of aerobic organisms capable of harnessing that oxygen for far more energetic metabolisms.
You also have the miracle of endosymbiosis, the theory championed by Lynn Margulis, which explains how complex eukaryotic cells formed. An ancient cell literally swallowed a smaller, free-living bacteria, but instead of digesting it, they formed a symbiotic relationship. That swallowed bacteria eventually became the mitochondria, the powerhouse of our cells. We know this is true because mitochondria still carry their own distinct circular DNA, completely separate from the DNA in your nucleus.
It is a testament to the messy, contingent history of biology. And understanding how deeply life is interwoven with Earth's history is the only way we can begin to search for it elsewhere. If we want to listen for another biology on one of those 6,333 exoplanets, what does an alien greeting actually look like?
It is not going to be a radio transmission saying, "Hello, people of Earth." An alien greeting is probably going to look like a subtle chemical imbalance in an atmosphere. We are searching for biosignatures and technosignatures.
A biosignature is an atmospheric gas, or a combination of gases, that strongly suggests biological activity. The classic example is the simultaneous presence of methane and oxygen. In a standard chemical environment, these two gases react and destroy each other very quickly. If you point a telescope at an exoplanet and see large quantities of both, it means something is actively, continuously replenishing them against the laws of chemical equilibrium.
And on Earth, that's life.
On Earth, that something is the global biosphere. A technosignature would be evidence of engineering, like industrial chlorofluorocarbons or artificial illumination on the dark side of a planet.
But the danger of false positives is immense. Just because we see methane doesn't mean we found space cows.
Absolutely. The need for rigorous context is paramount. Methane can be produced completely abiotically, without life, through geological processes like serpentinization, where water reacts with certain types of iron-rich rock deep underground. To claim a biosignature discovery, finding a suggestive molecule is only step one. You must have multiple independent lines of evidence, and you must exhaustively rule out every single geological or photochemical alternative. As of today, no extraterrestrial life has been confirmed.
Think of it like hearing an incredibly unusual sound while hiking in a deep forest. Your initial reaction might be, "That's a brand new species of bird." But hearing it is just the beginning. You have to prove it wasn't the wind whistling through a hollow branch. You have to prove it wasn't a rusty piece of farm equipment miles away. You have to prove it wasn't a glitch in your recording gear. Discovery starts with attention, but it requires the rigorous exclusion of all other possibilities.
And to hear that faint, unusual atmospheric note across trillions of miles of space, we need unprecedented technological eyes. Which brings us to the most powerful tool currently at our disposal, the James Webb Space Telescope, JWST.
Webb is a true marvel. But to understand why it's so revolutionary, you have to understand how it operates. It doesn't just see farther than Hubble. It sees a universe that is completely invisible to our human eyes. Webb operates in the infrared spectrum.
Infrared light is essentially heat radiation. To capture it, Webb requires extreme engineering. It has a massive 6.5-meter segmented golden mirror, but more importantly, it cannot orbit the Earth like Hubble does. It is stationed at the L2 Lagrange point, 1,000,000 miles away from Earth.
Why there?
A Lagrange point is a gravitational sweet spot where the pull of the Sun and the Earth balance the centrifugal force of the spacecraft's orbit. It allows Webb to stay in a stable parking spot while keeping the Sun, the Earth, and the Moon constantly behind its massive tennis court-sized sun shield. That shield drops the temperature of the telescope's instruments to near absolute zero. It must be perfectly cold. If the telescope were warm, its own infrared heat glow would blind its sensitive cameras.
So why go through all that trouble to see in the infrared? What are the superpowers of infrared light?
First, as we discussed with the Milky Way, infrared light passes straight through cosmic dust. Webb can pierce the dark molecular clouds and literally watch protostars forming in their stellar nurseries. But the second, deeper reason is cosmological redshift.
The expansion of the universe.
Yes. The universe is expanding, and space itself is stretching. When light from the very first galaxies formed billions of years ago travels toward us, it travels through expanding space. As space stretches, the light waves are stretched along with it. What started as visible or ultraviolet light gets stretched so much over billions of years that its wavelength drops all the way down into the infrared by the time it reaches Earth.
Oh, wow.
By designing Webb to see infrared, we are literally building a machine capable of looking back in time to the cosmic dawn.
And what it has found is shaking up astrophysics.
Yeah.
It's finding incredibly rich, mature populations of galaxies far earlier in the universe than our current models predicted. And it's finding supermassive black holes in the early universe that grew much faster than we thought possible. But we shouldn't jump to the headline that Webb broke cosmology. The physical universe didn't break. Our models were just incomplete. Surprises refine the models. They don't automatically overthrow the foundations of physics.
Science anticipates surprise. If we built a $10 billion telescope and it only confirmed what we already knew, it would be a failure. The unexpected data forces our astrophysical assumptions into sharper testing. It makes our understanding of reality more accurate.
And as we look to the furthest edges of reality, we also have to look to our immediate future, the next shore of human exploration. We have the Artemis program preparing to return humans to the moon for sustained operations. And naturally, the conversation shifts to Mars. But what I appreciate is moving past the marketing slogans. Mars is not a backup planet. Sending humans there is an almost insurmountable cascade of severe challenges.
Mars exploration demands profound respect for biology and engineering. It is not just a cold desert. The surface is bombarded by cosmic radiation because Mars lacks a protective magnetic field. The soil is laced with toxic perchlorates. The dust is electrostatically charged, razor sharp, and will infiltrate every mechanical seal and spacesuit joint.
It sounds like a nightmare.
It is extremely hostile. The atmosphere is too thin to easily land heavy payloads, but thick enough to burn up a spacecraft. Keeping humans alive requires flawlessly closed-loop life support systems where every drop of sweat, water, and breath of air is recycled for years.
The further our machines reach and the harder it becomes to survive out there, the more these discoveries reflect a question back toward Earth. We spend all this time looking outward, but ultimately, astronomy provides a cosmic perspective on ourselves.
That perspective is the culmination of this entire journey. We are not separate from the things we study. The atoms in your blood, the physical laws governing the neurons firing in your brain to process this conversation, they all belong to the exact same universe. We are the universe observing itself.
And realizing how vast the void is doesn't make human life meaningless. When you realize that Earth is the only world we know of that can currently sustain us, and that biology is incredibly fragile, our planetary responsibility becomes infinitely more urgent.
We use the exact same astronomical tools to protect the launch pad. The spectroscopy and orbital mechanics we use to map exoplanets and black holes are the identical tools we use right now to monitor Earth's changing climate from orbital satellites. They are the tools we use to scan the sky for hazardous near-Earth asteroids. The scale of the work demands international cooperation because the evidence and the consequences cross all borders.
It's a philosophy of disciplined uncertainty. We measure, we challenge, we refine. And mistakes aren't erased in shame, they become instructions for the next generation. I think this is a perfect moment to respectfully acknowledge the inspiration behind the text we've been exploring, Cosmos. A companion journey is an independent piece of work, but it stands on the shoulders of communicators like Carl Sagan, who has generations realize that science isn't just data, it is a deeply human story of survival and curiosity.
Wonder begins the search, but evidence gives that wonder direction.
As we wrap up this deep dive, I